I want you to imagine, just for a moment, trying to conduct a symphony orchestra, but this is not, your standard orchestra.
Right.
Imagine there are a million musicians sitting in front of you, and every single one of them speaks a completely different language.
It's a nightmare scenario.
Oh, it really is. And just to make it utterly impossible, the sheet music they're reading from, it changes every single millisecond.
Yeah.
So you wave your baton, and by the time your arm actually comes down, the strings have swapped instruments with the percussion. The brass section has split into 5 different groups.
Yeah.
And the entire composition has just rewritten itself.
Completely chaotic.
Exactly. That absolute overwhelming dynamic chaos. That is the reality of modern software architecture today.
It's a staggering image, honestly, but from an engineering perspective, it is entirely accurate. I mean, the sheer volume of communication happening behind the scenes of, well, the applications we use every day, it has vastly outpaced human comprehension at this point.
Yeah, it really has.
A single tap on your screen might trigger, thousands of background events across hundreds of servers.
Which is just wild to think about. So today, for our deep dive, we are looking at research that proves human engineers can no longer keep up with the scale of the systems they have built.
We really can't.
We are diving into a comprehensive presentation. It's by lead authors Dilip Kumar Pandiya and Nilesh Charankar, and it's titled Integrating AI into Distributed Microservice Architecture.
A very technical title for a massive paradigm shift.
Right, because what they lay out is huge. We're moving well beyond the limits of manual orchestration and exploring how, machine learning, predictive analytics, neural networks, how all that is transforming rigid code into self-healing autonomous ecosystems.
Yeah, what they call the intelligent hive.
Yes, the intelligent hive. And our mission today is to understand exactly how that works.
It is a foundational text for understanding where the internet is actually heading. I mean, for the past decade, we have been building larger and more complex distributed systems.
Right.
But Pandiya and Charankar, they argue that we have hit a cognitive wall. The complexity has it's exceeded our biological limits.
Wow.
We can no longer manage these systems manually. We have to build systems that manage themselves.
Okay, let's unpack this. Because I know when we hear AI, it is incredibly easy to just think of, chatbots generating text or algorithms creating synthetic images for social media.
Oh, absolutely. That's the popular view.
Yeah, but we are not talking about the surface level application of AI here. We are talking about the actual structural foundation of the digital world.
The plumbing, essentially.
Yeah, the invisible plumbing. We need to understand how we go from humans frantically trying to conduct that million-piece orchestra to the orchestra essentially conducting itself.
And to really grasp the magnitude of that shift, we have to understand the evolutionary timeline of software architecture first.
Makes sense.
We have to look at how the system broke in the first place, which is what forced us to invent this intelligent hive.
Right. Because before you invent the airplane, you have to understand why driving a car across the ocean doesn't work.
That's a great way to put it.
Let's go back to stage 1 then.
The monolith.
Ah, yes. The monolith. This represents the static era of software development. In a monolithic architecture, you have a centralized code base.
Okay.
Everything. I mean, the user interface, the business logic, the database access, the payment processing, user authentication, it's all tightly woven together into one massive single executable file.
When you say tightly woven together, what does that actually look like for a developer sitting at a keyboard?
It means that a developer working on, let's say, the shopping cart feature is opening the exact same massive project file as the developer working on the user profile feature.
Oh, wow. That sounds messy.
It is. They share the same memory space, the same processing resources, and crucially, the same deployment cycle.
So if the entire application has 10 million lines of code, you are deploying all 10 million lines every single time you make an update, even if you only changed, a typo in a single word of text.
I used to think of a monolith as a house of cards, but that's almost too fragile of an image.
Yeah, but too delicate.
It's more like a massive single-engine cruise ship.
Right.
It is huge, it is impressive, and it holds a lot of people.
Sure.
But if the main engine block cracks, the entire ship loses power. The restaurants shut down, the lights go out, the navigation fails. Everything is dependent on that singular, massive core.
That is a much more accurate mechanical analogy because everything is interconnected. A monolith has incredibly poor scalability.
How so?
Well, let's say your application is an e-commerce site And it's Black Friday. The checkout service is getting absolutely hammered with traffic, right?
Right, everyone is buying things.
But the update profile picture service, barely being used at all.
Makes
In a monolith, you can't just add more computing power only to the checkout service. You have to duplicate the entire massive cruise ship.
Oh, I see.
You have to spin up an entirely new instance of the whole application, wasting massive amounts of resources on services that don't even need scaling.
And beyond the wasted resources, the authors point out the high risk of deployment downtime, right?
Yes, exactly.
Like, if that developer makes a tiny syntax error in the billing module, they run the risk of crashing the entire application for everyone.
Precisely. And the industry realized this centralized model just wasn't sustainable as the internet scaled to, billions of users.
Yeah, it just couldn't hold up.
Which led us to stage 2. Standard microservices. This is the decentralized era.
Okay, the decentralized era.
Instead of one giant cruise ship, the industry decided to build a fleet of thousands of highly specialized independent speedboats.
I like that.
We broke the application down into dozens, hundreds, or even thousands of tiny independent pieces.
And Pandiya and Charankar provide a really brilliant breakdown of the anatomy of what they call the modern microservice node.
They do. It's very clear.
They divide this autonomous unit into 4 distinct layers. And I want to spend some time here because this is the absolute foundation of everything that comes next.
We definitely should.
If we don't understand the node, we cannot understand the Hive.
Yeah.
So layer 1 is the interface, or the APIs.
Right. The interface is the communication protocol. It is the agreed-upon language for how this specific node talks to the outside world and, to other nodes in the fleet.
Okay.
And the key concept here is loose coupling.
Loose coupling, meaning they don't depend on each other's internal mechanics.
Exactly. Service A doesn't need to know what programming language Service B is written in.
Oh, really?
Nope. It doesn't need to know what server it's running on either. Service A just sends a formatted message to Service B's API, and it expects a formatted message back.
Like sending a letter in the mail.
Exactly. The internal workings are completely hidden behind that interface.
Okay, then we drop down to layer 2. The logic or the service itself?
This is the brain of the node. This is where the actual computational work gets done. It is the decentralized business capability.
Right.
And the crucial architectural design principle here is called single responsibility. A single microservice should do one thing and do it perfectly.
So keeping with the e-commerce idea, you have one speedboat whose only job in the entire world is to calculate sales tax based on zip codes.
Yes.
That's it. It doesn't process credit cards. It doesn't check inventory. It just takes in a zip code and an amount, and it spits back the tax.
That is the perfect implementation of single responsibility.
Got it.
And then layer 3 is what allows that logic to run safely anywhere.
Which is the engine.
Layer 3 is the engine, specifically containers. The presentation mentions technologies like Docker or Podman here.
I want to dig into containers because I hear that word constantly in tech circles.
It's definitely a buzzword.
Yeah, and I always imagine a literal steel shipping container. But what is it actually doing on a server?
It is an isolated runtime environment. See, before containers, we used virtual machines.
Okay.
A virtual machine simulates an entire physical computer. It includes a massive, heavy operating system like Windows or Linux, just to run a small piece of code.
That sounds like overkill.
It was incredibly wasteful.
Yeah.
A container, on the other hand, shares the host server's operating system kernel, but packages up the application logic along with the exact specific libraries and dependencies it needs to run.
So instead of giving every single speedboat its own massive redundant engine room, they all share the fundamental infrastructure, but they operate in perfectly sealed off, identical environments.
Exactly. A Docker container guarantees consistent deployment. It ensures that the exact code environment that worked on a developer's local laptop will behave identically when pushed to a massive cloud cluster at, say, Amazon or Google.
Oh, that's huge.
Yeah, the environment inside the container is immutable.
That brings us to the final layer, layer 4, the storage or the databases. And there was a phrase used here in the research that I find fascinating, polyglot persistence.
Polyglot persistence. Yes, it's one of the most powerful and arguably most complex benefits of decentralization.
What does it actually mean?
It basically means decentralized data management. In the monolith era, the entire cruise ship shared one massive database, usually a highly structured relational SQL database.
Okay.
Every piece of data had to fit into strict, rigid tables.
Like a massive Excel spreadsheet where every single column has to be perfectly defined.
Yes, exactly like that. But polyglot persistence allows every single microservice to choose the optimal database type for its specific individual needs.
So they aren't all forced into the same spreadsheet.
Right. You don't have a central lock. So the financial transaction service might still choose that highly structured, secure relational database to ensure every penny is tracked perfectly.
Sure, that makes sense for money.
But the user's social feed service, it doesn't need rigid tables. It might use a flexible document database, like a NoSQL database, which is much faster for unstructured data like comments and tags.
So we shattered the monolith. We have these 4 distinct layers: the API interface, the single responsibility logic, the isolated container engine, and the specialized database.
Yeah.
We have independent deployability, we have polyglot persistence, we fixed the massive scaling bottleneck. This all sounds incredibly elegant.
It was a massive leap forward.
But here is where I have to pause and push back on the premise of this entire paper.
Okay, let's hear it.
If we solve the scaling bottleneck and everyone is working independently in their own perfect little isolated containers, shouldn't things be easier?
You would think so.
I feel like we just invented a new problem to solve an old one. Why fix what isn't completely broken?
Yeah.
Why do we suddenly need this massive, complex, intelligent Hive layer of AI on top of it?
That is the exact right question to ask, and it highlights a fundamental truth about software engineering. Every solution introduces a new set of trade-offs.
Always a catch.
Always. Decentralization absolutely solved the scaling bottleneck. You could finally deploy code independently, but in doing so, it created a massive complexity trap.
The complexity trap.
Yes. Because when you break a monolith into 1,000 microservices, you no longer have one application to monitor.
Right.
You have 1,000 independent, moving applications that must constantly communicate with each other over a network. You traded the internal fragility of a single block of code for the external chaos of 1,000 nodes shouting at each other simultaneously.
Okay, so we solved the traffic jam by giving everyone on the highway their own personal helicopter.
That's a terrifying thought, but yes.
But now we have 1,000 helicopters flying blindly in the same airspace, trying not to crash into each other while shouting directions back and forth.
That is exactly the reality. Every time a node has to talk to another node, the data has to travel over a network. That introduces latency, the physical time it takes data to move over a wire.
Okay.
It introduces the risk of dropped packets, network timeouts, and cascading failures. The orchestration overhead became monumental.
Which sets the stage perfectly for the core focus of the author's research. Stage 3. AI-enhanced ecosystems.
The autonomous era.
Yes. The shift from a chaotic swarm of helicopters to an intelligent hive, where the system continuously learns, adapts, and routes itself.
But to truly grasp why that AI is necessary, we need to look much closer at how those nodes are actually talking to each other. We need to understand the language of the swarm.
This brings us to a fascinating section of the presentation. The API Protocol Diagnostic Matrix.
Yes.
We mentioned earlier that layer 1 of a microservice is the interface, the API. But the authors make it very clear that not all interfaces are created equal.
Definitely not.
The way nodes speak to each other fundamentally alters the performance and scalability of the entire system.
The authors grade 4 main communication protocols, specifically on a matrix of performance versus scalability. And the mechanics of how these protocols move data explain why the system is currently choking on its own complexity.
Let's go through these because the technical differences here are huge. The first protocol is REST. It is described as the stateless request response model.
REST is the standard workhorse of the modern internet. When you open a web page, you are almost certainly using REST.
Okay.
It operates on standard HTTP verbs get, post, put, delete. It is excellent for general web services and basic CR operations, create, read, update, delete.
But the authors grade REST at 50% for performance and 75% for scalability. Why such a mediocre performance score?
Because of how it formats and fetches data, REST typically uses JSON JavaScript object notation.
Right, I've seen JSON files.
JSON is a human-readable text format. It uses curly brackets, quotation marks, and plain English strings to define data. For example, it will literally spell out, quote, name, unquote, colon, quote, John, unquote.
Which is great if a human developer needs to read it to debug a problem.
Exactly. But it is incredibly inefficient for a machine to process. When a server receives a JSON payload, it has to dedicate CPU cycles to parse that string of text, character by character, searching for the brackets and quotes to understand the structure before it can even read the data.
Oh, that sounds tedious for the computer.
It is. And worse, REST is highly prone to overfetching or underfetching.
I've heard an analogy for this before, and it really helps me visualize it. REST is like ordering from a very rigid set menu at a restaurant.
Okay, let's hear it.
You sit down, and you ask the waiter for the chicken. But the REST endpoint is designed to return the full meal object. So they bring you the chicken, but it comes with a massive side salad, a bowl of soup, and a dessert that you didn't even want.
That is overfetching. You requested a tiny piece of data, but the server sent you a massive, bulky JSON text file filled with data you will just throw away that consumes massive network bandwidth.
Right. Or, conversely, underfetching. You want the chicken, but the REST endpoint only gives the main course.
Right.
So you have to make 3 separate, entirely new network requests to the waiter just to get your drink, your fork, and your napkin. Each request adds latency.
Exactly. The rigidity of the endpoint and the bulkiness of human-readable text parsing drag down its performance. Now, to solve that exact over-under fetching problem, developers often turn to the second protocol in the matrix, GraphQL.
GraphQL is described as a single endpoint query language.
Yeah.
And according to the authors, it allows for exact client data requests.
Correct. Instead of hitting multiple different REST endpoints, a client sends one complex query to a single GraphQL endpoint. It is highly specific.
So, moving from the rigid set menu to a custom buffet, you walk up with your plate and you request exactly 3 carrots, 1 specific piece of chicken, and a half glass of water.
Exactly.
You get exactly what you asked for, nothing more, nothing less. It seems like that should solve all the performance issues.
You would think so, but interestingly, the authors still grade GraphQL at 50% performance and 75% scalability, exactly the same as REST.
Wait, why? If you are sending smaller, exact payloads over the network, shouldn't the performance skyrocket?
Because you shifted the burden from the network to the server's CPU.
Ah, I see.
In GraphQL, the server has to run a resolver to parse that highly complex custom query, figure out exactly which underlying databases or microservices hold those specific carrots and that specific chicken, stitch all that disparate data together perfectly on the fly, and then send it back.
That sounds like a lot of work for the server.
It is. The computational overhead to dynamically build that custom plate every single time is massive.
Okay, you save bandwidth, but you burn processing power. This brings us to the third protocol, and this is where the entire game shifts.
Yes, it is.
The protocol is gRPC, and the authors give this a massive 100% for performance and 100% for scalability, a perfect score. What is gRPC doing on a mechanical level that makes it so vastly superior?
gRPC abandons human readability entirely. It relies on 2 massive optimizations, HTTP2 and protocol buffers.
Let's break those down. What does HTTP2 do?
Older HTTP protocols process requests sequentially. You ask for an image, you wait, you get the image. You ask for a text file, you wait, you get the text file. It blocks other requests.
Like waiting in line.
Yes. HTTP2 allows for multiplexing. It can send and receive dozens of distinct data streams simultaneously over a single persistent network connection.
So instead of a single-lane road where cars wait in line, it's a massive multi-lane superhighway where data flows concurrently. And protocol buffers.
Protocol buffers, or protobufs, replace JSON. Instead of sending bulky text strings with brackets and quotes, gRPC serializes the data into a highly compressed mathematical binary format.
Okay.
Both the sender and the receiver have a precompiled schema, a decoder ring, essentially.
So instead of sending an English letter that the server has to open, read word by word, and interpret, you are sending a compressed mathematical shorthand.
Exactly. The machine doesn't have to parse text strings. It reads the binary instantly. It is blindingly fast, highly compressed, and designed specifically for low-latency machine-to-machine microservice communication.
Wow.
A human cannot read a protobuf payload, but the machines can process millions of them in a fraction of a second.
It's pure, unadulterated efficiency. Finally, the authors include one more protocol in the matrix, SOAP.
Yes, Simple Object Access Protocol.
But its scores are the lowest on the board. 25% for performance and 50% for scalability. If it's so terrible, why is it even in the presentation?
Because of legacy enterprise systems and absolute rigid security, SAP relies on XML, which is even heavier and bulkier than JSON.
Ooh.
It wraps every single message in complex, standardized security envelopes, something called WS security. The sheer size of the XML data being transferred is massive, which creates terrible latency.
So, if gRPC is a superhighway, SAP is an armored truck moving at 10 miles an hour.
Yes. It is heavily fortified. It takes forever to load the XML payload. It moves slowly, but you know for an absolute fact that the cargo is secure and will arrive exactly as intended.
Okay, that makes sense.
That is why it is still the backbone of legacy financial transactions and heavily regulated enterprise banking.
Okay, so let's zoom out and look at the whole picture. We broke our monolithic cruise ship into 1,000 microservice speedboats. Some of these speedboats are communicating using bulky REST text strings. Some are using heavy SOP armored trucks. Some are firing laser-fast binary gRPC signals. And they're all doing this millions of times a second across a network.
And that reality is what creates the microservices complexity trap. The authors map out this trap into 4 distinct quadrants, illustrating exactly why human oversight has failed.
Quadrant 1 is network latency and communication failures. We touched on this, but let's dive deeper into the mechanics of a failure.
In a distributed system, a single-user action like clicking purchase might require service A to talk to service B, which talks to service C, which queries database D.
Okay.
If service C experiences a minor network timeout, just a split-second delay, service B has to wait, service A has to wait.
It's a traffic jam that cascades backwards.
Precisely. These cascading timeouts tie up server resources, and eventually the whole system grinds to a halt. And tracing the origin of that failure through 1,000 interconnected nodes is like trying to find a single broken wire in a city-sized electrical grid.
Which leads directly into Quadrant 2, data consistency. This goes back to our polyglot persistence discussion, right? Everyone has their own database.
This is one of the hardest problems in distributed computing. In a monolith, you have a single database. When a transaction happens, it uses ACD principles, atomicity, consistency, isolation, durability.
Okay, ACD.
The transaction either 100% succeeds and writes to the database, or it 100% fails and rolls back. There is no gray area.
But in microservices, if service A updates its database, but service B's database is temporarily unreachable over the network, you have a split brain.
Exactly. You are forced to rely on complex eventual consistency models. The system basically says we updated database A, and we promise we will eventually update database B when the network reconnects.
I feel like we see this all the time as users. Have you ever liked a post on social media, refreshed the page, and your like briefly disappeared before coming back a second later?
That is eventual consistency in action. You queried a database node that hadn't received the synchronized update yet. Managing that uncertainty across financial or healthcare data is a massive complexity trap.
I can only imagine. Quadrant 3 is security attack surfaces.
Right. In a monolith, you have a few main entry points to secure. It's a fortress with a big front gate.
Okay.
In a microservice architecture, every single independent API endpoint is a door. You multiply the surface area for potential vulnerabilities by 1,000. Every node must constantly authenticate every other node.
And finally, Quadrant 4, monitoring overload.
This is the breaking point for human engineering. Every microservice generates logs. Every container generates metrics. Every network hop generates trace data.
It's just too much information.
Way too much. The sheer volume of telemetry data generated by thousands of distributed nodes vastly exceeds human diagnostic capacity.
The authors make a very blunt statement here in the research. They state, human engineers cannot monitor 1 million state changes per second.
It is the pivotal thesis of the entire paper. The architecture has explicitly demanded an intelligent orchestrator. You cannot manage distributed chaos with manual human oversight.
Right.
The system has evolved beyond our biological ability to track it in real time.
So if human cognition is the bottleneck, we have to inject machine cognition. We need to inject the hive mind.
Exactly.
But this is the part where it usually sounds like pure science fiction. People throw around the word AI like magic pixie dust that fixes broken code. But how exactly do the core principles of AI physically map onto this chaotic architectural framework?
What's fascinating here is how Pandiya and Charankar demystify the AI. They don't treat it as a monolithic black box that just thinks.
That's refreshing.
They meticulously map distinct AI mathematical disciplines to distinct structural architectural needs. They break it down into 3 highly specific pillars.
Let's go through these 3 pillars because this is where the theoretical becomes structural. Pillar 1 is machine learning, specifically applied to automated testing and bug prediction. How does this actually work mechanically?
It operates through historical pattern recognition on the codebase itself. Machine learning algorithms ingest vast repositories of git commit histories.
Okay.
They look at every single line of code ever written, modified, and reverted in the system's history.
Like a massive digital forensic audit.
Exactly. By analyzing millions of past pull requests, the ML models learn the subtle structural patterns that correlate with failures.
Wow.
When a developer writes a new piece of code, the ML doesn't just check if the syntax is correct. It calculates a probability matrix.
What does that mean?
It might say, based on historical data, when a developer modifies this specific legacy database query while simultaneously updating the payment routing logic, there is an 87% chance of a memory leak.
Oh, that's incredibly specific.
It predicts the likelihood of deployment failure before the code is even compiled.
It is essentially learning from a decade of human mistakes to secure the future.
Beautifully put.
Pillar 2 is neural networks, specifically deep learning. The application here is anomaly detection and performance optimization.
This is where we move from analyzing static code to real-time observation of the living system. The authors highlight two very specific mathematical structures of neural networks here. First, autoencoders.
What exactly is an autoencoder doing in a microservice mesh?
An autoencoder is an unsupervised learning model used for anomaly detection, primarily for security. It works by taking normal network traffic, compressing it down into a tiny, dense mathematical representation called a latent space, and then trying to reconstruct the original traffic from that compressed space.
Okay, wait, walk me through that. Why compress and reconstruct it?
Because the model is trained exclusively on millions of normal, safe network requests, it gets exceptionally good at compressing and reconstructing normal behavior.
Ah, I see.
But the moment a hacker sends an anomalous payload, a strange API request, a weird database injection, the autoencoder tries to compress it and reconstruct it, but it fails. The reconstruction error spikes massively.
Because it doesn't know how to reconstruct something it has never seen as normal.
Exactly. It flags the traffic instantly. It doesn't need a signature of a known virus. It simply recognizes that this payload fundamentally deviates from the mathematical baseline of normal.
That is incredibly elegant. And the second type of neural network mentioned is LSTMs.
Long short-term memory networks. These are a specific type of recurrent neural network designed specifically for time series forecasting.
Time series forecasting.
Yes, they possess an internal state or memory that allows them to understand sequences of data over time, not just isolated snapshots.
How does that apply to a chaotic server environment?
In this architecture, LSTMs monitor the telemetry data we talked about: CPU usage, memory consumption, network latency. A traditional monitor only alarms when a threshold is crossed, like when CPU hits 99%.
Right.
An LSTM looks at the subtle degrading latency trends over hours or days. It might notice that a memory garbage collection cycle is taking 2 milliseconds longer every hour.
And it connects the dots.
Exactly. It forecasts that trajectory and predicts a catastrophic crash hours before the system actually hits the breaking point.
Okay, those first two pillars, machine learning for bug prediction and neural networks for real-time anomaly detection, make logical structural sense to me.
They do.
But pillar 3 is the one I immediately had a visceral reaction to. Pillar 3 is natural language processing, or NLP. And the application the authors list is requirements analysis and interface generation.
I can see why that gives you pause.
Let me push back hard on this. Are you telling me that the AI is parsing unstructured, messy user stories?
Yeah.
Does that mean the AI is reading plain English documentation written by a project manager and converting it directly into hard-coded architectural domain boundaries? Because let's be honest, business analysts write terrible vague requirements.
It's true. They often do.
Someone writes a paragraph that says, make the user profile faster and more social. How can an AI possibly translate that vague English into a rigid microservice boundary without creating an absolute disaster?
Your skepticism is entirely justified, and it points to the hardest problem in software engineering: translating human intent into machine execution. But here's the mechanism of how NLP is bridging that gap. The NLP isn't just reading make it pop and writing code. It is performing deep semantic extraction.
The semantic extraction, how does that work?
The NLP models tokenize the unstructured text. They use named entity recognition to map the nouns in the business document, words like customer, invoice, shipping address, into distinct data entities.
Okay.
It maps the verbs purchase, update, cancel into expected CR-root operations.
So it's breaking down the grammar of the business request into a technical blueprint.
Exactly. It cross-references this extracted semantic map with existing domain-driven design boundaries in the current architecture. The AI doesn't unilaterally write the code, it generates an architectural proposal.
Oh, a proposal.
Right. It says to the human architect, Based on the frequency of the word invoice interacting with shipping in this document, I propose we split the billing service away from the logistics service to avoid a bottleneck, and here's the generated gRPC interface protocol to connect them.
Okay, that changes things. It's not a magic code generator. It's a massive analytical engine that reads the blueprint and helps you draw the actual structural floor plan based on semantic logic.
Precisely. It acts as the bridge between human business needs and technical execution.
So we have this hive mind conceptually installed. We have ML predicting bugs, autoencoders guarding the gates, LSTMs predicting crashes, and NLP helping design the boundaries.
A very capable Hive.
But how does this intelligence actually direct the massive flow of traffic in real time? How do we move from looking at static maps of microservices to a living, breathing GPS system?
This requires a transition from traditional routing to what the authors call intelligent service discovery.
Let's establish the baseline. In a standard non-AI microservice setup, how does traditional routing work?
Traditional routing relies on fixed configurations. Usually it involves static IP addresses or hard-coded DNS registries. When user request A comes in, the API gateway looks at a static table that says, forward this to the server located at IP address 192.168.1.5.
It's like having a physical address book. You look up a name, you drive to that exact house. But what happens if the container crashed and was moved to a different server? And what if the road is blocked?
The connection simply fails. You get a 404 error or a timeout. It is rigid and incredibly fragile in a dynamic, containerized environment where pods are spinning up and down every minute.
Right.
The intelligent Hive, however, abandons fixed IPs in favor of dynamic discovery via an intelligent service mesh.
The authors detail 3 AI mechanisms driving this dynamic discovery. The first is clustering algorithms.
Instead of human engineers manually tagging and categorizing services, the AI uses unsupervised clustering algorithms, conceptually similar to k-means clustering.
How does that work?
It observes the behavioral traits of the services in real time. It looks at their payload sizes, their query frequencies, and their active dependencies.
So it's not grouping them by what they are named, it's grouping them by what they actually do.
Exactly. It might organically realize that the inventory service and the shipping estimation service communicate back and forth 500 times a second.
Ah, okay.
It dynamically clusters them logically within the network topology, facilitating instantaneous low-latency discovery. It groups them by behavioral proximity.
The second mechanism is reinforcement learning. Now, I know reinforcement learning is how AI learns to play chess or video games by trial and error. How does it apply to routing network traffic?
The exact same mathematical principles apply. In reinforcement learning, you have an agent interacting with an environment trying to maximize a reward.
Okay.
Here, the AI orchestrator is the agent. The microservice network is the environment. And the reward function is minimizing latency and maximizing successful throughput.
So it's constantly testing the waters.
Constantly. It uses an exploration versus exploitation strategy. It routes 95% of traffic down the known fast paths, that's exploitation. But it routes 5% of traffic down alternative experimental network paths, that's exploration.
That's clever. If an experimental path encounters a network bottleneck, the algorithm penalizes that path. If a new, faster path is discovered because a node was less busy, the algorithm updates its routing tables and rewards that path.
Wow.
Through continuous trial and error at a scale of millions of requests per second, the AI learns the absolute most efficient topology.
It is essentially a living GPS that reroutes traffic not just based on where the traffic jam is right now, but where it might be in 5 seconds.
Which brings us to the third mechanism, predictive registration.
This ties right back into those LSTMs, right?
Yes. The AI anticipates which backend services will be required based on upstream traffic spikes. If the front-end login servers suddenly see a 300% spike in traffic, the AI doesn't wait for those users to hit the database query service.
What does it do?
It proactively registers and buffers new database connections before the users even make the request.
That proactive approach transitions us perfectly into the next major concept in the paper: predictive orchestration and self-healing.
It's a game changer.
Because managing traffic isn't just about finding the right address, it's about actively managing the volume of cars on the road and the health of the vehicles. The authors detail 3 ways the AI orchestrator manages the physical nodes themselves. The first is predictive autoscaling.
To understand this, we have to look at the flaw in traditional reactive autoscaling. Normally, you set a strict metric threshold. You tell the system, if the CPU usage on the billing service hits 85%, spin up another container to handle the load.
That sounds reasonable in theory.
In theory, yes. But spinning up a new container takes time. Maybe 10 seconds, maybe 30 seconds. By the time the CPU hits 85%, triggers the alarm, and waits for the new container to boot up, the CPU has already hit 100%.
And things are freezing.
Exactly. Your users are already experiencing massive latency.
I compare reactive autoscaling to turning on your windshield wipers after you are already completely soaked by a thunderstorm. The damage is done.
That is an excellent analogy. Predictive autoscaling, driven by those time series AI models, moves us from reactive thresholds to proactive provisioning.
So the system anticipates the rain, pulls up the meteorological radar, and physically puts an umbrella over your head before the first drop even hits you.
Precisely.
The AI forecasts the load trajectory and provisions the necessary computational capacity before the latency hit ever occurs.
Exactly. It ensures the capacity is waiting for the user, rather than making the user wait for the capacity. The second orchestration method is intelligent load balancing.
How does that differ from standard load balancing? Don't we just pass the incoming traffic down the line?
That is standard round-robin load balancing. You have server 1, server 2, and server 3. Request A goes to 1, B goes to 2, C goes to 3, and D goes back to 1.
Right.
It is entirely blind to the actual health and processing queue of those servers. Server 1 might be bogged down processing a massive complex query, but the round-robin balancer will still blindly throw another request at it just because it's its turn.
Which creates a massive bottleneck on server 1 while server 2 is sitting idle?
Precisely. Intelligent load balancing analyzes the real-time queue depth, memory pressure, and predicted future capacity of every single node. It routes traffic dynamically to the node that is mathematically most capable of handling it at that exact millisecond.
And the third piece of this orchestration puzzle is perhaps the holy grail of system administration: self-healing clusters.
This is the ultimate realization of the autonomous ecosystem. We discussed how autoencoders detect anomalies. When the AI detects that a specific container is beginning to behave erratically, maybe a slow memory leak is causing its response time to degrade over the last hour, the orchestrator doesn't just send an alert to a human engineer and wait.
It takes action.
It acts autonomously. The orchestrator actively drains the network traffic away from the sick container, gracefully shuts down the corrupted pod, provisions a brand new, healthy container from the immutable Docker image, and reroutes the traffic to the new node.
That's incredible.
It essentially performs microscopic surgery on its own infrastructure, replacing failing organs in real time without a single human intervention.
Okay, let's summarize where we are, because this is mind-bending. We have an architectural system that uses machine learning to predict bugs in the code. It uses natural language processing to understand English business requirements.
Yes.
It routes traffic using trial and error reinforcement learning. It scales its servers proactively before traffic hits, and it actively euthanizes and replaces its own corrupted servers in real time. It's absolutely incredible. But it raises a massive logistical question for me.
How do you actually build it?
Exactly. If this ecosystem is so tightly woven, so fast, and so self-optimizing, how does a human developer safely introduce new code into it? If I write a new feature, how do I push it into this autonomous Hive without the Hive treating my new code like a virus and attacking it?
This brings us to the operational heart of the presentation: the intelligent assembly line, or the AI-enhanced CI/CD pipeline.
CI/CD stands for continuous integration and continuous deployment.
Right. It is the automated infinity loop of modern software development. Continuous integration means multiple developers are constantly merging their code changes into a central repository.
Okay.
Continuous deployment means that code is automatically built, tested, and pushed into the live production environment.
The presentation breaks this loop down into a sequential cycle: code, build, test, deploy, monitor, release. Let's walk through how AI supercharges this assembly line, starting at the very beginning with code review automation.
In a standard workflow, a developer writes code, submits a pull request, and waits hours or days for a senior engineer to manually read it and look for mistakes.
Sounds slow.
In the intelligent Hive, the moment the code is submitted, AI-driven SaaS static application security testing takes over.
How does SAST actually analyze code it has never seen before?
It parses the code into an abstract syntax tree, or AST.
Right.
It breaks the code down into its fundamental logical structures. It doesn't just look for typos. It analyzes the data flow paths.
Oh.
It looks for complex vulnerabilities like SQL injections or cross-site scripting, the kind of threats outlined in the OWASP Top 10 framework. The AI checks these structural paths against millions of known vulnerability patterns and immediately flags security flaws before the code is ever even compiled.
It's an automated security audit taking place in seconds. Next on the loop is predictive bug detection. We touched on this with the ML pillar, but how does it integrate into the pipeline?
As the code moves to the build phase, the algorithms analyze the cyclomatic complexity of the new code, essentially measuring how many different branching paths and if-then statements exist.
Okay.
Highly complex code combined with a high historical churn rate files that are constantly being changed and breaking triggers a severe warning. The pipeline will literally halt the build and demand a human review if the predictive matrix determines the code is too statistically risky to proceed.
If it passes that check, we move to testing. And the authors outline intelligent test generation.
This solves one of the biggest bottlenecks in software delivery. Traditionally, as an application grows, its automated test suite becomes massively bloated. Every time you push a minor update, the system might run 10,000 automated tests, taking hours of compute time.
And most of those tests have nothing to do with the one line of code you just changed.
Exactly. AI dynamically maps the specific code path that were altered in the new commit, and it dynamically generates and selects only the specific test cases required to validate those exact paths.
That's so efficient.
It utilizes concepts like mutation testing to actively try and break the new code, ensuring maximum coverage without the bloated execution time.
And the final piece of the testing phase highlighted here addresses front-end development, visual UI and self-healing tests.
This is a phenomenal application of computer vision AI. It solves a notorious headache called test flakiness.
What makes a test flaky?
In traditional UI testing, the script looks for a rigid, hard-coded DOM locator like an XPath that says, click the button at div tag 4 span 2. If a front-end developer moves that button just 2 pixels to the left or changes the invisible ID tag, the functionality is completely fine, but the rigid automated test fails. It throws a false negative.
Which halts the entire pipeline for no actual reason.
Right. But AI tools, like Apple tools mentioned in the research, use visual computer vision algorithms. They don't look at the rigid DOM code, they look at the rendered pixels.
They actually see the page.
They do. They understand the structural relationship of the web page visually. If the button moves slightly or changes color but maintains its semantic purpose, the AI recognizes the superficial change, automatically updates the test locator dynamically, and lets the test pass. The tests literally heal their own scripts.
So the assembly line itself is actively intelligent. But getting the code perfectly compiled and tested is only half the battle. You still have to push it into the live Hive.
Yes, the deployment.
You have to release it to the users. And that brings us to predictive analytics and deployment success. The authors outline a deeply complex process involving canary deployments.
A canary deployment is a crucial risk mitigation strategy in distributed systems. Instead of taking the old software down and releasing the new software to 100% of your users simultaneously, you route a tiny fraction of live traffic, say 1% of users, to the new version. They are the canary in the coal mine.
And in the intelligent Hive, the AI acts as an active toll gate during this canary deployment, using ML health metrics to perform automated canary analysis. How is the AI analyzing that 1%?
It is continuously statistically evaluating complex telemetry. It compares the new canary service's performance against the established baseline performance of the old service in real time. Crucially, it isn't just looking for outright error codes or crashes.
What else is it looking for?
It is looking for deeply subtle degradations.
Like what?
Like a database query that suddenly takes 4 milliseconds instead of 2, or a memory heap that is accumulating data 5% faster than the baseline. If the statistical algorithms detect an anomaly that crosses a confidence threshold, the AI acts instantly. It triggers an automatic rollback.
Meaning it pulls the plug on the new code.
Yes. It seamlessly routes that 1% of traffic back to the old, stable version. The users barely notice a blip, and the developers receive a highly detailed diagnostic report of why the canary failed.
And if it succeeds?
If the baseline remains statistically normal over a set period, the AI orchestrates a phased rollout, dynamically shifting 10%, then 50%, then 100% of the traffic to the new code.
And the research notes that the AI also calculates optimal deployment timing based on historical usage patterns, predicting the exact temporal windows where a rollout will cause the absolute minimum disruption to global traffic.
The pipeline ceases to be a passive conveyor belt. It is an active, judgmental gatekeeper.
Okay, we've talked about all these amazing capabilities conceptually. Let's ground this in reality. Let's look at the actual software tools powering this. The presentation provides what they call an AI-powered tooling stack layer cake.
It is incredibly important to demystify this by looking at the concrete, commercial, and open source tools being utilized by enterprise architects right now.
Let's start at the very top layer, sitting right in the developer's IDE, code generation and assistance. The tools listed here are GitHub Copilot, Tabnine, and Gemini.
These are large language models deeply integrated into the development environment. They provide context-aware code completion.
Context-aware.
Because they have massive context windows, they understand the surrounding architecture. As a developer types a function name, the AI synthesizes boilerplate code, generates complex regular expressions, and even writes unit tests automatically, drastically reducing the manual syntax labor.
The next layer down is security and vulnerability scanning. The tools are SNCC, Deep Code, and checkmarks.
These are the engines behind the SASCI automation we discussed. They perform deep semantic code analysis. SNCC, for example, maps the entire dependency tree of an application.
Yeah.
If you import a third-party library that imports another library that contains a known zero-day vulnerability, these tools detect that deeply nested threat and provide automated code remediation snippets to patch it before compilation.
Then we have testing and quality assurance, featuring tools like Apple Tools and Testum.
These handle the visual regression computer vision and the self-healing UI test lifecycle management.
And finally, the foundational layer, the heavy engine of the layer cake, machine learning frameworks. The authors list TensorFlow, PyTorch, and scikit-learn.
These are the foundational mathematical libraries. Data scientists and ecosystem architects use these frameworks to design, fine-tune, and ultimately deploy the custom autoencoders and LSTMs directly into the microservice mesh.
Right.
These are the tools used to actually build the Hive mind's analytical core.
So we have the phenomenal tooling stack, we have the judgmental intelligent CI/CD pipeline, but you still need a foundational blueprint. You can have the most advanced automated hammer and laser-guided saw in the world, but if your architectural blueprints are fundamentally flawed, the building will still collapse under its own weight.
Oh, absolutely.
How do you design an architecture from scratch that maximizes these AI enhancements while avoiding the classic traps of distributed systems?
This is where Pandiya and Charankar transition from mechanics to philosophy. They outline 4 core design principles for the intelligent hive. These are established software architecture patterns, but the authors explain exactly how AI fundamentally enhances and elevates each one.
The first principle is domain-driven design, or DDD. Conceptually, this is about aligning microservices to actual, real-world business capabilities, right?
Yes. The goal of DDD is to define strict bounded contexts. The inventory system should have its own data and logic entirely separate from the user management system.
And we touched on this earlier. The AI enhancement for DDD is utilizing natural language processing to analyze business documentation. It helps architects mathematically determine those bounded contexts based on semantic frequency, rather than just human intuition, ensuring they don't split a single cohesive capability across too many fragile network hops.
Exactly. The second principle is event-driven architecture, or ED.
How does ED differ from standard API communication?
Standard API communication is synchronous and tightly coupled in time. Service A asks Service B for data and has to wait for a response.
Right.
In an event-driven architecture, communication is asynchronous, utilizing a message broker like Apache Kafka. When a user buys a product, the checkout service doesn't directly call the shipping service. It simply publishes an event to a central ledger saying, "Order 123 was paid."
And then any service that cares about that event can just listen to the ledger and react on its own time.
Precisely. It decouples the services entirely. The AI enhancement here is profound. Machine learning continuously monitors that massive central stream of millions of events.
Oh, wow.
It dynamically optimizes the partition routing of the message broker to prevent bottlenecks, and it uses anomaly detection to spot fraudulent or malformed events before they are consumed by downstream services.
Principle 3 is the API gateway pattern. We briefly mentioned the gateway earlier. It serves as the single point of entry for user traffic.
Rather than external users trying to authenticate and connect directly to hundreds of internal microservices, all traffic hits the API gateway. The AI enhancement transforms this simple router into an intelligent, active shield.
The research lists 3 specific AI functions at the gateway: predictive rate limiting, dynamic protocol translation, and real-time threat blocking. Walk me through the dynamic protocol translation.
This goes back to our protocol matrix. An external mobile app might send a bulky JSON-based REST request to the gateway because that's easy for the app to generate.
Sure.
The intelligent gateway intercepts that REST request, uses AI to perfectly map the JSON payload, dynamically translates it into a hyperfast binary gRPC protocol buffer, and fires that binary into the internal microservice mesh.
Wow. It translates the slow external language into the fast internal language on the fly.
Exactly. And the fourth principle is the circuit breaker pattern.
Like a physical circuit breaker in my house. When too much electricity flows, it snaps to prevent a fire.
The exact same concept. In software, a circuit breaker is a state machine, closed, open, or half open. Normally, it is closed, allowing network traffic to flow.
Yeah.
If a downstream service fails repeatedly, say it times out 5 times in a row, the circuit breaker trips and becomes open. It immediately halts all traffic to that failing service, returning an instant error to the user rather than forcing them to wait for a timeout.
Which prevents the cascading traffic jam we talked about earlier.
Right. But a traditional circuit breaker only trips after the massive failure has already occurred. The AI enhancement applies those predictive LSTMs directly to the circuit breaker logic.
So it predicts the short circuit.
The algorithms trip the circuit predictively before the failure cascades based on the subtle degradation of latency trends. It recognizes the mathematical shape of a crash before the crash physically happens, isolating the node proactively.
Okay, these blueprints sound incredibly robust. But I have to ask the realistic, cynical question. What happens when a human architect inevitably gets it wrong? What if they completely ignore domain-driven design and decide to break a simple application into 1,000 incredibly tiny microservices just for the sake of it?
That is a highly common scenario, often referred to as microlithic architecture. And the authors address this reality with a direct breakdown of architectural pitfalls and their corresponding AI-driven mitigations.
Let's run through these pitfalls. Pitfall number 1, overly fine-grained services. Basically exactly what I just described. Too many tiny services creating massive network latency because they have to talk to each other constantly just to complete a basic task.
The AI mitigation for this is continuous topology analysis. The orchestrator uses graph theory to monitor the inter-service chat continuously. If the AI sees that the calculate tax service and the calculate shipping service communicate with each other 10,000 times a second and rarely talk to anyone else, the AI will flag this inefficiency. It will recommend to the architect that those two services be merged back together into a slightly larger service, eliminating the massive network latency penalty.
Pitfall number 2, inadequate inter-service communication leading to bottlenecking.
If the services are communicating inefficiently, the AI mitigation is the intelligent mesh. We utilize AI to dynamically alter the routing paths, perhaps shifting communication from REST to an event-driven broker like Kafka, actively bypassing congested network nodes to prevent the bottleneck from forming.
Pitfall number 3, ignoring security practices across vast independent attack surfaces.
The AI-driven threat mitigation model addresses this by enforcing a zero-trust architecture automatically. Because there are thousands of endpoints, static passwords or API keys are useless if stolen. The AI uses those autoencoders to detect anomalous payload structures and erratic access patterns in real time. Every single request between every single node is continuously authenticated and authorized based on behavioral context, instantly blocking any request that deviates from normal behavior, even if it has the correct password.
And the final pitfall, lack of proper monitoring and diagnostic capacity.
This is solved by deep AIOps integration. We move entirely away from passive logging, where human engineers desperately search through millions of text files using Controlled F after a catastrophic crash.
Yeah, it sounds painful.
We move to active anomaly detection. The system monitors its own telemetry and flags issues before they become critical.
So we've zoomed all the way in. We looked at the specific nodes, the binary communication protocols, the mathematical neural networks, the active CI/CD pipelines, and the foundational design patterns. Now it's time to zoom all the way out. We need to look at the final overarching picture. And we need to ask the biggest, most existential question of all. Where does the human actually fit into this autonomous hive?
The authors present a final visual synthesis in their research called Synthesis, the autonomous ecosystem. It beautifully and structurally ties together every single concept we have discussed today into one cohesive flow.
Let's trace that synthesis flow from start to finish. External user traffic flows into the AI-enhanced API gateway. That gateway intelligently translates, secures, and distributes the traffic into the microservice mesh.
Yes.
That entire sprawling mesh of nodes is continuously monitored and dynamically routed by the centralized AI neural network, the AIOps orchestrator. And that orchestrator continuously feeds performance data and failure predictions back into the CI/CD pipeline to judge and improve future code deployments.
If we connect all of this to the bigger picture, we arrive at the profound underlying system insight of the entire presentation.
What's that?
In this architecture, AI is not a single isolated service. It is not an add-on feature like a chatbot widget on a website. It is the fundamental connective tissue of the infrastructure. By integrating AI at the bedway, within the service mesh routing, and throughout the CI/CD deployment pipeline, the architecture fundamentally changes its nature. It ceases to be a static, rigid collection of code files. It becomes a continuous, self-optimizing organism.
A self-optimizing organism.
Yeah.
That is a massive conceptual leap from a house of cards or a cruise ship, and it leads directly to the author's final critical point, the evolution of the developer.
Yes. If the system is automatically writing boilerplate code via LLMs, dynamically generating its own test suites, optimizing its own network routing, and physically healing its own broken containers, what is left for the software engineer to actually do?
Here's where it gets really interesting. The presentation contrasts the historical role of the manual coder with the future role of the ecosystem architect. And here is where I think the industry is going to experience the most friction. The basic day-to-day act of writing software is fundamentally shifting.
The role of human engineering is shifting aggressively away from writing manual syntax. As AI automates the repetitive generation of standard logic, testing, and deployment mechanics, human focus must move to strategic system design.
So as an ecosystem architect, my job is no longer focused on typing out a flawless for loop or writing a perfectly optimized SQL database query or manually configuring an Nginx routing table.
Exactly. The machine is vastly superior at those microscopic tasks. Your job becomes macro-level orchestration.
Okay.
You are focused on utilizing domain-driven design to establish robust, loosely coupled business boundaries. You are focused on training highly specialized AI models, say, building a finely tuned autoencoder specifically for identifying healthcare fraud, or an LSTM tailored for predicting latency in high-frequency trading networks.
Oh, that's fascinating.
You define the parameters, and you deploy those models as autonomous agents within the secure data mesh. The human provides the overarching strategic vision, defines the business outcomes, and sets the ethical and operational guardrails. The AI handles the intricate, million operations per second execution and orchestration.
And the authors state clearly, this transition is the ultimate advantage for modern enterprise. Organizations that adopt these AI-driven microservice principles won't just write software faster. That is a dangerous oversimplification.
Right.
They will build resilient autonomous systems that can actually survive, scale, and adapt in an increasingly chaotic and hostile digital landscape.
So what does this all mean for us? Let's take a breath and recap this incredible journey. We started with the fragile, static monolith, the giant centralized code base where a single typo could bring down the entire system.
Then we moved into the decentralized chaos of standard microservices. We solved the scaling problem by breaking the code into isolated containers, but we created a terrifying complexity trap.
We did.
We traded internal fragility for massive network latency, data consistency nightmares, and monitoring overload that no human brain could possibly manage. We looked at how protocols like REST struggled to keep up, and how binary data streams like gRPC became necessary. And finally, we arrived at the solution, the intelligent Hive.
The final stage.
We saw how machine learning predicts bugs by analyzing Git histories. We saw how autoencoders detect anomalies and LSTMs predict server crashes. We saw how natural language processing actually helps define architectural boundaries. The AI dynamically routes traffic using reinforcement learning, self-heals broken containers, and acts as a ruthless gatekeeper in the CI/CD pipeline.
It is, without hyperbole, a comprehensive roadmap for the inevitable future of enterprise architecture.
And this matters deeply to you, the listener, regardless of your role.
Yeah.
If you are a back-end engineer, your career trajectory is shifting right now from writing syntax to architecting these ecosystems.
Absolutely.
If you are a business leader, the financial resilience and scalability of your entire operation depend on migrating to these autonomous principles before the complexity trap crushes your infrastructure.
It's unavoidable.
And even if you are just an everyday user, you need to understand that you are benefiting from these invisible, intelligent systems every single time A social media app seamlessly scales to handle a massive viral event, or a banking app self-heals a broken database connection before it ever throws an error on your screen.
We have fundamentally moved from building rigid, static structures to cultivating dynamic, living environments.
Which brings us right back to our opening hook. We started by imagining a symphony orchestra with 1 million musicians speaking different languages, reading sheet music that changes every millisecond. We thought it was utterly impossible to conduct. But the reality is we aren't trying to be the conductors anymore. We are stepping back. We are becoming the composers.
We write the thematic parameters, we define the instruments, and the orchestra intelligently manages its own performance.
Which leaves us with one final provocative thought to mull over as we close. If artificial intelligence is actively writing the code snippets, dynamically generating the test suites to validate that code, continuously routing the live network traffic based on its own trial and error learning, and deciding entirely on its own when to merge or separate foundational microservices to optimize its own topology, at what point does a software application cease to be a tool that we build and start becoming an independent digital organism that you merely collaborate with?
That is the profound and perhaps unsettling reality of the intelligent hive.
Thanks for joining us on this deep dive. Keep questioning the code.